Hello, welcome to today's video. Today we're going to address some urban scanning radar technology. I'm going to give Mark the floor now, so I'm going to remain quiet for a bit, but here we go. Enjoy the video.
Hi everybody. Right, well, as you'll see, this is the equipment that's been fitted by councils across the country. This is shared as we've had a whistleblower send us the information, and obviously we've got a box delivered by a whistleblower at one of the councils, alright? Because obviously the people are very concerned in the lighting departments about what this equipment is, and I've been asked to actually review it. Because this is a weapon system, alright? It's nothing more than a weapon. Now I know it's masquerading as a light, but it's a weapon. This is the Harvard piece of technology. Obviously, that's the antenna. That's a scanner, it's radar. It's a radar piece of equipment, you can see that. This has got the 450 volt capacitor on it. And you see the cabling. It's really important to see that cabling. This is the delivery system, alright? About what this is. Let's just show people this is not a dipole antenna. Look. It's a high gain dielectric lens antenna, alright? It's in a little bit better shape than the other one that we've shown the video on, but that is an illegal piece of equipment. It's not a Part 15 FCC approved piece of equipment. This can target acquire. It's radar. That's a scanner, alright? It's a scanning antenna. They are illegal. Anybody thinks that councils have the right to scan into your home are mistaken. That's an offence in law. Alright, let's just pop that back. The delivery system to the weapon. Alright, that's the delivery system to the weapon. This is the cabling, because I've had a couple of foolish people, absolute ignorance. That's the cabling to the LED streetlights. As you'll see, they're very thin. They're not that thin because they don't carry a great deal of power and they won't burn out. However, this piece of cabling, pretty powerful stuff, and it has to be because you've got a 450 volt capacitor in this bit, but you've also got a number of 450 volt capacitors on the board. These are not for the LEDs. This is the LED delivery system.
Okay, so clearly we're dealing with someone who doesn't understand that you need to build redundancy with capacitance and also stuff like relay switches. If you've got a 3 kilowatt load that needs switching, you're not going to have a relay that's bang on 3 kilowatts. You're going to have a 5 kilowatt relay or a 6 kilowatt relay. It's just redundancy. It's a bit of headroom. It's built into all modern electronics. Okay. So in this video, we're going to be looking at this WiMAC LeafNode. 868 megahertz output, reasonably powerful MCU, not particularly. Yeah, so we've got a SAW filter and we've got a TCXO crystal. Actually, probably the reason why they fitted a TCXO crystal in here and not just some cheap off the shelf, because I've had a quick look over this board and the redundancy in this board is it's really good. I mean, they've made this, to either fail to safe or not to fail at all. It's really well designed, albeit over-engineered and complex for what it needs to do. I mean, considering, I've got the same SI1000 chip there. Yeah, and to be fair, if I was mass producing this, I'd want to go for lesser quality components. But we must admit, WiMAC, they have gone above and beyond with this unit in terms of reliability, and it's just its functionality. But one of its biggest drawbacks for this unit is the fact that this antenna, for one, is terrible. Terrible antenna design. Albeit it works, quite a good ground plane on it, but yeah, I mean, helical antenna would be ideal for this application. It's just basically really weak as a transmitter. It's a receiver, yeah, but this unit primarily is a receiver. We can tell this because we have a LNA amplifier there, so that's like a preamp or input amplifier. So this unit is primarily designed to listen. It gives a data burst back, 64 bytes packet, Manchester encoded data burst, just to say hello, I'm here. It gives that data burst, then the branch node will communicate back and give it further instruction. This chip really, from my dealings with this in the past, it's not very good at sustained transmission, especially with the FSH, FHSS transmissions. It's really not that good to sustain them for any kind of amount of time. I'm assuming I've not even checked this out and not seen its spectrum yet, but I'm assuming if I blink, I'll miss the actual transmission from this device once I get it up and running. So a few things to note that are clear and obvious if we reverse over. We've got a smoothing capacitor going from the positive negative rail. We've got a PWM controller down there, switching MOSFET. Yep. Usually a PWM is 3V 3 volt, so I'm assuming then that this flyback transformer has multiple taps and multiple windings inside. So if you look carefully there, that trace goes back to this PWM area here. So I'm assuming this flyback transformer pushes a 3V3 DC back out to it, which brings me round to the fun side. So our positive comes in on this pin here. It goes through one diode, two diode, and then this really cool with the redundancy is all these resistors in parallel here. If one of them resistors goes, the unit will still keep functioning. Same for the ceramic noise cancelling caps here. That one of them fails, it's more than enough to keep going. So this is fully rectified. This is the positive pad. Then that positive pad feeds this flyback transformer. So I'm assuming then it's going to be rectified down to about 10 volts DC, looking at the size of this transformer. There's a 3V3 coming back out on this winding here, on that going from one of the individual taps of the windings inside, to that PWM. The PWM then fires the switching MOSFET. Large separation between the actual MCU voltage and the input voltage. It's not as large as I'd expect for 240 volts, so my suspicions are correct. It's between 100-ish volts and 120 volts in, looking at just the size of the components really, and this flyback transformer is teeny to handle 240. There's quite a bit of rectification going on. It's fully rectified, but still, I mean, yeah, you'd be hard pushed to put 240 through this. So I'm assuming then that the ballast itself regulates this voltage down to about 110 volts. That's just my initial observation. The actual amplification of the signal is more low noise amplifier in. Got SAW filter as well to get any noise out there. So all the instructions come from this EEPROM, which is SPI. I know this is SPI for the EEPROM because I've worked with these transceiver chips before. for these MCUs before. So looking at that, that's probably 8 megabyte. So what that'll do, that'll hold the instructions. So these effectively, when they're in situ, there'll be like something that size, a handheld, and it'll either go up in a cherry picker or if they can do it from the ground. I've never actually witnessed that. They will key in to the unit and assign it somewhere on the frequency spectrum its own little place in time. And that unit will have all the FHSS data, so it'll say, well, you can hop X through Y and then you can hop A through B. I know it doesn't work like that, but that's just a generalization and an overview of what that little unit would do, or at least the instructions it would give. Inside the chip, there will be a pre-programmed instruction set, which then will write that to the SPI module and update whatever YMAC has already done in the factory. Done this in circuit in the factory or whatever. So, okay, what we're going to do then, we're just going to test these voltages, see if my theory's right. And probably this antenna, I'm going to take this antenna off because that's dangerous if I'm doing testing live voltages and I catch that. Yeah. Make for a great video, but sadly not from my perspective. Oh yeah, so PWM as well. We've got PWM signal. I'm assuming that's going to be UART 1 wire, so it comes through. Yeah, so it'd be some pin on this side of the chip. Like that, trace maybe. Anyway, so it comes out the low voltage side and goes back down here, through there, and the orange, that's the data line. So I'm assuming it's UART. I mean, it could be a PWM signal, I suppose, but I suppose it's going to be driven by UART. So what will happen? There'll be a pulse, probably on the leading edge of the clock. Fire that down. There'll be another receiver module in there, which is probably the actual PWM module. So that'll receive an input signal. The pulse will be determined to a duty cycle. So, so many percent or the duty cycle itself, however they've calculated it and whatever interface peripheral they're using. But I'm assuming it's UART. One-way UART, sends pulse. Because I don't think there's anything PWM on this side of the board, other than that's on this PWM to drive that switch. So let's give feedback from the transformer, obviously. Yeah. So yeah, it's probably UART. Probably. It's not going to be SPI because we're using a lot of the SPI for the instructions in our EEPROM. So yeah, it's going to be UART or some other one-wire protocol. Goes off and fire the def rate up in 3, 2, 1. Cool. Okay, we are now live. Great. Okay. So this is our live pad here, and this is our negative. Now, what we don't want to do today is link the live pad with the UART 1 wire that sends the data back to that device. So the nearest one is negative. Right. So I'm going to go for positive N. Oh, tricky one. There we go. Negative. This conformal code. Oh, conformal. Oh, bugger. This conformal coding is a nightmare. Absolute nightmare. See, it's giving wrong readings already. There we no, conformal coding to the rescue. There we go. So 106 volts. in. That's pretty bang on to what I estimated it would be. Yep, 106 in. Okay, so what we're going to do now is this pad here. This is after the rectification of the voltage in. So we get a good. It's so hard to get a good go with that. I don't think that's quite right. I think this conformal coating is giving us some trouble. There you go. 11 volts. So, yeah, nearly 12. So it's 12 volts after rectification. Yep, that's stable now. Really pushing these pins in. I've taken some conformal coating off. But it's a nightmare. It really is. Cool, yeah. So 110-ish volts in, and it gets rectified and then goes through. I'm just going to switch that off for a second. And what I'll do, I'll just discharge. Yep. We'll take that off. Yes, 110 volts come in, it gets rectified, smoothed, and then we go. This is our positive rail that we just tested, so that's 12 volts ish into this flyback transformer. So I'm assuming then, we'll fire this back up in a minute and test it this side round. That should be 3 volts out from that winding. So 2 volts. Oh, there you go, 3.1. So we're factoring a little bit of conformal coating. Yeah, if I push them in. So that's 3 volts. Back to that PWM module, turning that off. Excellent. So, yep, checking that's off again. The theory was right. It's fully rectified in, smoothed, and smoothed again. Right, okay, so we're in DC mode now. We're just looking the other side of this flyback tranny. Cool, okay. I've noticed there's a small voltage regulator there. So I'm assuming these are going to be slightly higher than I anticipated. So 5 volts maybe on the other side of them diodes. But I think once it goes through this little tranny here, because that's the main voltage onto the chip, it's going to be 3V3 and 1.2 volts. So let's have a mooch of that. So got a nice big fat ground plane. Okay, so let's conformal coating. 6 volts. Right, so this should be 6 volts on this side of the transformer. We can get beyond the conformal coating. Oh, yep, 6 volts. Okay, there we go for the other side of this now. I'm showing the right leg. Oh, 3.3 volts. So this MCU uses 3.3 volts, but that's no surprise to me. It may be a surprise to some people out there who thinks this is some kind of death ray perhaps. So let's see what the other voltages are in this regulator. Oh, yeah, on that. Come on, oh, 1.2 volts. Okay. Let that discharge safely over there, you know, with this being the death ray capacitor. Ooh. Okay, so that's, the voltage is conclusive there. 110 in, gets rectified down to 12 volts, gets smoothed, and the noise taken out. It goes through the flyback tranny, through these 2 diodes, 2 separate streams of voltage at 6 volts. The cap will be the same as well, 6 volts. It comes around the circuit through this capacitor, which is probably smoothed even more. Goes into this voltage regulator, goes in at 6, and we've conclusively proven it's 3 volts one side, 1.2 the other, which adds up to what these chips need. And like the SAW filters 3v3, the TCXO 1.2. So that's primarily why there's a lot of smoothing or deaf-ray competitors on this device. It's because it doesn't like the noise. Hence why they've used a TCXO, not a normal crystal, because a normal crystal, you can imagine this, because it's the side the antenna would be on before I took it off, this butted up against the cold plastic shell. That cold plastic shell, could have 4 inches of snow in it. It could be minus 20 degrees. Most crystals don't like low temperatures, whereas a TCXO is really good at operating down to like minus 40 and still producing the clock needed for the processor and the RF unit. Yeah, I mean, there's nothing more to say about this than what I've already said. I'm reverse engineering this, just the voltage. I mean, I'm no big Clive, but I can see a bridge rectifier. I can see resistors in parallel and series. So there's redundancy if one goes. There's redundancy in the diodes as well. There's further redundancy in smoothing capacitors. There's redundancy coming out here. Got 2 packages of diodes. Redundancy 2 caps. The only thing really that might be affected is the voltage regulator, but it's smoothed and such a consistent 6 volts that I can't see that really giving out in a hurry, because it's doing a very, very minuscule job of 3v3 and 1.2 volts for the MCU and the MCU peripherals. The 1.2 volt actually could be for the low noise amplifier input. I'll have to reference that. I'll find out what this chip is. This RF switching chip, because that switches between the low noise input and obviously when it transmits. So there is a secondary RF pin which is pulled either low or high, which switches probably a small transistor over in there, which allows transmission, and then switches over. It's probably capable of simultaneous transmission, actually. I could be backing the wrong tree there, but I'm assuming that transmitter switch, so there'll be a slight delay between transmitting and receiving, which makes this not radar. Yeah, well, everything about it makes it not a radar. Right, so the time's come. Let's have a look at the assembly in this SPI EEPROM. I'm going to extract that today. I'm going to use the in-circuit clips, and I'm going to use a Great FET, which is an absolutely amazing reverse engineering tool for hardware. This thing is quality. I've got various JTAGs. I've got like bus pirates, but the reason why I've put this on my reverse engineering board is because it just does everything. I've captured kind of bytes in flight from a keyboard, from SD cards. It's such a good reverse engineering tool. So yeah, okay. So red is pin 1. I know that to be pin 1. There we go. And as before, the conformal coating on this is a nightmare. Right, so I've just going to set Great FET to grab this flash chip. Excellent. So we have here, I've got 4 terminals open, all using Radar 2 to decompile some programs. I've got a Python program, wrote a Java one. This is the data we just captured. And I've also got a ODT, which is basically a Microsoft Word document. Cool, so I'm just setting the debugger to look for 8051 assembly, which is what our data is. I'm setting the analyze flags. And now getting that data. There we go. So this is all the assembly off that flash chip or that EEPROM. It's not exactly stunning, is it? I mean, it's certainly not radar. So there's various instructions, calling on various registers, which you would expect. I can't go too much into it because, I say, it's proprietary and these are still out there in the wild, so I'm not going to do a hacker's job. Hence why I'm blurring out the actual register jumps and instructions. Cool, I'm just going to look for some function blocks now. So you can see there's some function blocks, but there's no arguments at all. That's basically what 8051 is. So if we have a look now at our Python program, so setting the analyze flags, looking at our function blocks, you can see there is a couple of arguments for our Python program, which is expected. Now we're going to look at our Java program. Oh, yeah, I've got to point it at address. I'll probably come back to that in a minute. Forgot because it's Java. Everything about Java is terrible, but we can still see, the header file. These are just all the imports for the program. If you know Java, then you recognize them straight away. You can see there's quite a lot of data in comparison to our 8051 assembly. I shall come back to that function block in the Java to prove my point later. But for now, yeah, that's it. It's just like the header. Cool. Just looking at the hexadecimal values of that. I'm going to do the same here, actually. Look at the hex. Yeah, same again. So all the kind of the gold writing really is more like function based and the imports and all the kind of good stuff. But you notice in the 8051 there's not a lot of header data. So yeah, that speaks volumes about it. So I've got this I've got this Microsoft Word document.
It's science, all right?
Basically, set the analyze flag. I'm going to look for some functions, and there's no arguments or variables or anything. It is just generally data functions, references for the data that's been set in the header for the program. Yeah, so like I say, there you go. No arguments, no variables, because it is just assembly language. Cool. And you see there's actually, because there is data references, there's a lot more going on there than what there is in our assembly language. So this is just a comparison, basically, just a kind of a weight of bytes and, kind of any kind of data or function, kind of just a representation of that. Yeah, so what I'm going to do now, I'm going to go back and pull the arguments and have a look at functions. So I'm going to set a new address. Okay, analyze flag set, and oh yeah, excellent. Now we've found some arguments. Yep. So that's pretty straightforward. So yeah, I mean that's just obviously one address, but if I went through all the addresses, there'd be a F ton of data there. But I'm just doing this as a general overview, a comparison to the 805 assembly language. Cool. Right, so before I continue on with the video, I have to address RF radiation exposure for prolonged periods of time. It is an issue. Non-ionizing radiation is harmful in close proximity. So this is for the WiMAC. It's from the FCC official testing. You'll notice the bottom right-hand corner says I have to be about 20 centimeters away from the unit when it's transmitting. So let's have a look. Yep, you can see the don'ts and the do's there. Okay, that's pretty self-explanatory, right? And again, don't do that, but do that. Okay, moving on. Right, so what we're going to do now, we're going to measure and look at the signal being sent between the WiMAC units, or namely the SI1000 chip, and our SDI units. We're going to look at, obviously, there's not a lot of distance separation between these two. We're going to look at not so much signal strength, because that's neither here or there, to be fair with this unit. We're going to look at its bursts. So I reprogrammed the EEPROM and I added some extra instructions.
Science!
That controls the easy radio module inside after I decompiled it. So I reflashed the EEPROM with the extra instructions. So I can't exactly how many bursts it is. I think it's 7 or 8 bursts that it's going to give now. 64 bytes. And the whole shebang, really, the preamble, the works. It's going to do that about 8 times before powering down. Yeah, so I've set the R5.
All right.
I've changed the channel. What I've done in that respect is setting the
Science
to do it at 869.540 megahertz. It just seems to be out of range of anything in the area. There's a few spurious transmissions on 868. So I've set that register for that frequency. So okay, without further ado, let's get on with it. So I'm going to fire up the Harvard ballast, and then we should start to hear at least and see our transaction. 1, 2. Okay, so we're going to just analyze the signal now. Straight away, I'm not seeing any complex radar signals like a barcode-coded phase modulation waveform or anything like that. So we focus in. Yeah, straight away. That's Manchester encoding. This is a FSK transmission or modulation. Yeah, I'm not seeing any linear radar signals or ramp up there. So effectively, this isn't going to give a return. It can't give a return. Yep. So this is a actual radar return. You can see the pulse magnitude there and the actual phase of the pulse and everything. Nothing in there looks like that. Absolutely nothing at all. So in conclusion, is this a phased array radar? No, it's a switch to switch the lights on and off, or to dim them. Oh, the bullshit. The stench of it. Hope you enjoyed the video. More to come. Thank you.